In this video I want to look at vertical circular motion, following on from your study on horizontal circular motion. You should read the notes and examples on vertical circular motion really before you watch this video. I just want to pick out one or two important points just to highlight and work through a relatively straightforward example. This is just an introductory thing. So we're looking at objects moving in a vertical circle now, and this is restricted as far as our specification is concerned to cases where there is, because it's vertical, clearly there's going to be one vertically downwards weight force, which will be mg. So we have an mg force vertically downwards there. So it's restricted to that force and then just one other force, no more than one other force, and that other force will be directed along the line of the radius. It could be outwards from the circle in certain situations, which we'll look at in another video, but generally speaking, mostly it's going to be inwards, but it will certainly be directed towards the center of the circle. So that's the first key point to recognize. Second key point, different from horizontal circular motion, the speed now is not going to be constant. And that will have various implications for us, but it's important that we recognize that the speed is not going to be constant. This means obviously that the object is accelerating. It was accelerating in uniform horizontal motion as well, but now in horizontal motion we were just looking at a single component of acceleration, just the radial acceleration directed in towards the center of the circle. In vertical circular motion now we can have the acceleration in any direction at all. However, what we're going to do with the acceleration is we're only going to think of a component of it directed towards the center of the circle, and that will be exactly the same as the acceleration that you were using in horizontal circles. So there we are, we've got it there listed, either v squared over r for our acceleration or possibly r omega squared. Mostly, to be honest with you, we'll use the v squared r over r version. And the fourth point to recognize here is a crucial one which allows us to use particular techniques on vertical circular motions, and that is that radial forces do no work. And this is why we're restricting these situations to two forces, one vertical weight force and then one radial force. The vertical weight force, what we're going to do here is we're going to take an energy approach to analysing, or certainly to start analysing, our vertical circular motion. And we can do that because of this restriction on the number of forces and on the fact that the radial forces do no work. So if the two forces are a weight and one radial one, we've got weight, which we can account for in our work energy principle type of approach as just a change in gravitational potential energy, and we don't need to worry about any other form of work in that sense that it's doing. And then the only other force that we've got as a radial force, because the direction of motion of the particle is always around the circle, and therefore it's at any instant it's traveling in a tangential direction. That means that the radial force is perpendicular to the direction of motion, and therefore it does no work. And this is great because this allows us to, when we're thinking about a work energy principle type of approach to things, actually it means we can just do it as a conservation of energy. We can just equate changes in gravitational potential energy and changes in kinetic energy. Obviously, equal and opposite, so we will have either a gain in kinetic energy as the object goes down the circle and loses height, and therefore there is a loss of gravitational potential energy, or the other way around. It might start at the bottom of the circle with some speed, or somewhere down on the circle with some speed, with some kinetic energy, and it'll lose its kinetic energy as it goes up the circle, gaining gravitational potential energy. So it's just a case of essentially just either loss in GPE equals gain in KE, or the other way around, a gain in GPE is going to equal a loss in KE. So loss or gain in GPE equals gain or loss in KE. And that's because of this radial force not doing any work, so the total amount of mechanical energy in terms of gravitational potential and kinetic is going to be a constant. So general approach to vertical circular motions is to take this approach to the energy balance approach to establish either a value or an expression for the speed of the object at any particular point on its circular path. And then from there we can, if necessary, go on and think about forces, the radial force in particular, because once we've established v, then we can work out what the radial acceleration is by using v squared over r, and then we can use Newton's second law on it and all the rest of it. So a quick word about a quick example about how to use this. So here's an example, vertical circular motion, example 1. So we've got a particle with a given mass attached to a light rod. We'll think about the situations in a subsequent video. A light rod of length 0.2 meters, free to rotate in a vertical plane. And then here we go, here's the initial conditions. The particle is held at rest vertically above B, and it is slightly displaced so that it moves in a vertical circle. The implication of that last sentence there is that we're at the top of the circle, but we're not starting with any speed, we're starting with 0 speed. Essentially that's the point of this slightly displaced. We're not giving it any measurable amount of speed at the top, so we've got u equals 0 situation at the top. And then two things we've got to calculate: the speed of the particle it passes through, the lowest point of the path, and the tension in the rod at that point. Okay, so a conservation of energy approach to the in the first stage, where we want to establish the speed of the particle at the lowest point on the path. So this is going to be losing gravitational potential energy and gaining kinetic energy. So we've got loss in GPE, sorry about my writing, equals gain in KE. The loss of GPE, as always with gravitational potential energy, we can choose for ourselves where we want the 0 gravitational potential energy level to be. So if we choose the bottom of the circle here to be the 0 level, then that means we can just treat this as a single term thing rather than an MGH minus another MGH. We can just treat it as an MG delta H kind of thing. So this is just going to be a single term with the H there being the total height of the circle. So we've got loss in gravitational potential energy being mgh, gain in kinetic energy. So with the slight displacement at the top and 0 velocity, assuming a 0 velocity at the top, the gain in kinetic energy is just going to be whatever kinetic energy it has at the bottom, which is just going to be half mv squared. So we've got a nice straightforward equation just balancing out mgh with half mv squared. And in this nice simple one, the masses are going to cancel out, which is always nice. And then we can just, select that pen there. And then we can just rearrange this to make it say v squared equals 2gh, we can substitute some numbers in. So we've got a height loss rather, beg your pardon, height loss here of 2 radiuses. The and B clearly is going to be the centre of the circle. So A is starting 0.2 meters above B, and it's going to end up 0.2 meters below. So we've got a total height change of 0.4 meters. And so we can substitute that into our equation here for V squared. V squared is 2g times 0.4. And so that's 4g over 5, isn't it? From 2 times 0.8, sorry, 2 times 0.4 giving us 0.8, which is 4/5. So we're my preference for fractions here. So we've got v squared as 4g over 5, and that means that our speed at the bottom of the circle is just going to be the square root of that. So root 4g over 5, and if we calculate that as a decimal number, actually it comes out rather neatly as 2.8, and of course that's a speed which will be meters per second. So speed at the lowest point on the circle, 2.8 meters per second. And then we're also asked to calculate the tension in the rod at this point. So just a quick look back at the original diagram here. So presumably, if this is on a rod, there's going to be some tension in the rod. That's our radial force there, T, acting inwards. In a general position around the circle, what I'd be doing now is I'd be thinking about resolving my weight force into a radial and tangential component. Actually, in the question that we're looking at, the object has moved down to the bottom of the circle, and so those two forces are actually just going to be in line with each other, aren't they? So we've got a situation like this. Now there's the particle at the base there. Now I've got tension in the rod acting vertically upwards, and the weight force acting in line with it but in the opposite direction, vertically downwards. And all I'm going to do is just take a Newton's second law approach, F equals ma approach, to thinking about the radial forces and radial accelerations. So my acceleration is directed towards the radial acceleration directed towards the center of the circle, so I'm going to have towards the center of the circle as being my positive direction. So I've got T minus mg as my net force, an upwards T and a downwards mg, and that just needs to equal m. And for the A here, I can use my v squared over r. So I've got T minus mg equals mv squared over r. Quick rearrangement gives us a way of calculating T mg plus mv squared over r. And we've got numbers for all of those things now. We had a mass of, what was the mass? 0.5, wasn't it? So we can have T as a half g plus mass of a half, radius of 0.2, so that's a fifth, but we're dividing by that, so it's going to be on the top. So half times 5, and v squared we had up there as 4g over 5. Bit of simple cancelling out. So it gives us 2.5 g's, 5g over 2, and numerically that comes to 24.5 newtons.